All right, everybody, so here is our first section in your 1.3 notes. So these will actually take 2 days. And our essential questions for these 2 days are, how are measures of center and spread used? How are outliers determined? And what is a box plot? So this first set of notes here is mainly looking at this first essential question. So just a reminder that you should be writing all of these things down as you go, pausing as you need to, rewinding if you need to look at an example again. So you're not just writing, but you're actively learning with these notes as we go here. There will be some checks along the way. Make sure you stop and do those, then come back and check the answer to see where you are at. All right, so measures of center. We have two measures of center, and the first is the mean. So the mean is the average that you're used to seeing. The way we denote the mean is with x with a line on top of it. We pronounce that x bar. And x bar is just equal to the sum of all of your values divided by the number of values that you have. So that's the mean you're used to seeing there. So we refer to that as x bar. So for example, say we have this data set here and we want to find the mean. So this is where you get your calculator out and you're calculating the mean here. So we would simply add up all of these values and divide by 9, since there are 9 observations in this data set. All right, and we end up with x bar equals 5. So adding all those values and dividing by 9 gives me 5. All right, now here's a question to pose. What if we added an observation right to the end here? So what if I added in a 50? Okay, what would happen to my mean then? So 50, we're thinking is probably going to be an outlier here. It's much bigger than all the other values in the data set. So I want you to calculate the mean with this new observation in here. So adding up all those values, this time dividing by 10 instead of 9 because there are now 10 observations. And we end up with x bar equals 9.5. So even though it doesn't look like there's a huge difference between 5 and 9.5, before 5 kind of fell right in the middle of our data, or pretty close to it. Now our x bar is 9.5, which is kind of right in here. 9.5 is bigger than all but one of our observations, so that is a pretty significant change for this data set, going from 5 to 9.5. So we say that the mean is very sensitive to outliers. That means if I have an outlier in my data set, my mean is going to be way different than if I didn't have that outlier. So that's just what we were talking about. When we add that 50 in, it shot the mean up so far that it's now larger, but all than one value in our data set. Okay, another measure of center that we look at is the median. So median is just the middle value. If all my values were lined up in order from least to greatest, it's that middle value. And the notation we use for the median is just a capital letter M. All right, so this is that same data set still. We want to find the median. So here we have 9 observations. So my middle value is just going to be right here, right? I have 1, 2, 3, 4 on the left, 1, 2, 3, 4 on the right. So that 4 in the middle is going to be my median. So we say capital M equals 4. All right, so we want to kind of look at what we did with the mean as well. What happens if we added an observation of 50? Let me erase that. If I add in that 50. So this time, I don't have 9 observations. Now I have 10. So actually, my median isn't going to be one of these exact values, because to go in the middle, I'd have to look at 1, 2, 3, 4, 5. I'd have to look right here. So I now have 5 values on each side. So instead of circling a value, so this is what happens when we have an even number of observations. It goes between here. So I want to look at between 4 and 5. And exactly between 4 and 5 would be, well, we happen to have it right there as well, would be M equals 4.5. So my median, when I added in that 50, changed from m equals 4 to m equals 4.5. Okay, so not a big change here, right? So we say that the median is resistant to outliers, but the mean is not. So this word resistant is basically just talking about what happened when I threw that outlier in there. So the mean changed a lot, the median barely changed, so the median is resistant. Having that outlier in there didn't really affect it all that much. Okay, so next thing we're looking at, we looked at shape a little bit yesterday. We want to see how shape affects the mean and the median. So if a distribution is symmetric, we say that the mean and the median are equal to each other. All right. If my distribution is skewed to the right, my mean is going to be greater than my median. If the distribution is skewed left, we say the mean is less than the median. And here's kind of why in picture form. So if we are looking at this first graph here, so this one is roughly symmetric. I can tell, since it's symmetric, my middle value, my median, is going to be right in here, as is my mean, because it's symmetric, so my mean and my median are going to be equal, or roughly equal, we would say, right? Nothing's ever exactly symmetric if you're looking at real data. Next, then, we look at the graph that's left skewed. So if this is kind of my peak right here, so I know that that median is going to be, so now these may not necessarily be outliers, but my median is definitely going to be pulled that way, and so is my mean. Now, since the median is resistant, we say the median is probably somewhere in here, right? So if I find my peak, my median is going to be pulled since it's skewed to the left. My median is pulled just a little bit to the left, where my mean is pulled more so to the left. So these values that I'm marking aren't going to be my exact mean and median. This is just for relative position. So here's my peak. The median is a little bit to the left of it because median is just affected a tiny bit. But my mean is affected much more. So my mean is more to the left. So I don't know if it's this exact value, but I know it's to the left of the median, and the median is to the left of the peak. All right, skewed right works the exact same way, just towards the right instead of the left. So if I have my peak here, my median is going to be somewhere slightly to the right of the peak because I have these larger values in here that's going to pull those measures of center with it. Okay, the median not nearly as much, but the mean is going to be pulled even more to the right. All right, so next here, you guys have a check on page 53. So this is where you're going to pause. Go ahead and try that check on page 53. It's 3 problems. They give you a little stem plot on the left to answer 3 questions about, and then come back and see how you did here. All right, so let's see how you did on that check. So we've got a stem plot. The first is asking you, based on the stem plot, would you expect the mean travel time to be less than, about the same as, or larger than the median, and why? So what they're trying to get you to see here is the shape. So if you look at the peak would be around stem 1, and you have way more values to the right of that peak or below that peak than you do the left. So this graph would be skewed to the right. So we know that if something is skewed to the right, the mean is bigger than the median. So because the distribution is skewed to the right, the mean will be larger than the median. The second one then, use your calculator to find the mean travel time. So the way you would do that, you would have to add up these observations. So like my first observation, 0 with a stem of 5 is just 5. 1 with a stem of 0 is 10. So you would have 2 10s there, 4 15s, 3 20s, 125, and so on. So you would be adding up those values and dividing by how many there are, which they tell you there are 20 randomly selected New Yorkers. Right? So here our mean is 31.25 when you add up all those values and divide by 20. which is larger than the median they gave us of 22.5, which makes sense because our distribution is skewed to the right. Number 3 then, they want to know if the mean or the median would be a more appropriate summary of the center of this distribution. So now we want whatever that center is to kind of accurately reflect the middle. So what happens is if our distribution is skewed, the median is going to be a more accurate representation because if you have outliers in there, which we look like we could potentially have an outlier, the mean is going to be a lot more affected by that outlier than the median is. So because it's skewed to the right, we would say the median would be a more accurate representation. All right, next topic we're looking at here is standard deviation. So mean and median were both measures of spread, measures of center, excuse me. Standard deviation is then a measure of spread. So we'll look at a few different types of measures of spread in this section. Today we're just looking at standard deviation. So for mean we used X bar, median was a capital M. For standard deviation we just use an S, or sometimes you see an S sub X. Most of the time I just end up using an S though. All right, and the standard deviation measures the typical distance from the mean. So what you're looking at, if I have a set of data and I know what the mean is, about on average, how far are my observations away from the mean is what the standard deviations look at. So this is a pretty important sentence right here. Measures the typical distance from the mean. All right, now this is kind of referencing outliers here. So we know that the mean is sensitive to the outliers. Standard deviation is based off of mean because I want to know on average how far are my values from the mean. So because the mean is sensitive to outliers, standard deviation is also sensitive in outliers because they kind of go together there. All right, so if you have outliers, just know that your standard deviation is not going to accurately reflect all of your observations because you have that large one in there. All right, standard deviation is always greater than or equal to 0. So it's measuring your spread, how spread out your data is. If all of your observations are the same, so say I was looking at age of high schoolers and I happened to have a class of all seniors and they all happened to be 17 years old. So my data set would just be a bunch of 17s. My standard deviation would be 0. There's no spread there because they're all the same. If you made a dot plot, it would just be one giant tower of dots, right? They're not spread out at all. They're all together. The more the observation varies, the larger standard deviation becomes then. So say in that same example, maybe I'm looking at my AP Stats class that has juniors and seniors, so probably people 16, 17, maybe even 18 years old. So that spread's going to be bigger than 1. Now say I were looking at a class that had freshmen through seniors in it. So there my standard deviation is going to start to become even bigger because I have even more ages in there. They're becoming more and more spread out. This is just something to note and write down. We're not actually going to ever calculate standard deviation by hand. It's a pretty long calculation and your calculator can do it much, much quicker than we can. But to find standard deviation, you have to find something called variance first. And variance is just denoted as S squared. So that's just kind of a note to keep. They could potentially, I've seen on the AP test in a multiple choice question, they reference variance as opposed to square root. And all you need to know, or variance as opposed to standard deviation, and all you need to know is that S, or standard deviation, is the square root of variance, or vice versa. Variance is standard deviation squared. So you just need to know how to go between the two there. All right, so my on-screen calculator is not working, but here is how you find standard deviation in the calculator. So like yesterday when we were making the histogram, you would have to put your data all in a list, and you'll get a chance to do that here on a check. Once your data is all in a list, these are the buttons you're pushing. So the second and stat button. Yesterday when we did this, we went over to ops to sort our list from smallest to largest. You want to go over one more to math, where they ask you for, or they give you a few different options there. So notice the third and fourth option there are the mean and the median. So if you wanted to find the mean or the median this way of a data set, that would be fine. So instead of adding up all the values and dividing, if you had everything in a list, you could do it that way. But I want you to look down at the seventh one there that says standard deviation. So if you go to that and hit enter, you just have to tell it what list. So if all your data is in L1, you would push second and number 1. And that's how your calculator will give you standard deviation. Yep, so that's just saying this is also where you can find the mean and the median of your list. All right, so this is where you guys in your books are trying to check on page 63. So I wanted to change this a little bit. So they have some directions there. I just want you to find and interpret the standard deviation. So in your calculator, so plugging the values of the problem into the list and then going back to these steps right here. Okay, so pause this, go ahead and try that and come back and see how you did. All right, so finding S in the calculator should have given you 6.24 inches. So that's just saying on average, that's how far those values are from the mean. Okay, so that's about half a foot, so that's a pretty big difference. All right, so what this is telling us is, so this is the interpret part, the player's heights typically vary about 6.24 inches from the mean height, which is 75 inches if you were wondering. So 75 is going to be my mean, kind of my middle value there. On average then, so if I'm looking at all the players combined, on average their height was 6.24 inches away from that 75. So some are going to be shorter, some are going to be taller, some are maybe even exactly 75 or close to it, but on average they vary, so they're different from my mean by about 6.24 inches. All right, so you guys now have the 1.3 assignment. It says assignment 1.3 day 1, so we'll do some more 1.3 tomorrow. You just have to worry about the day 1 assignment for now. That's in Google Classroom.